everybody. Thank you all for braving the wild, catastrophic rain to come out here this morning. And welcome to a continuation of our talk on object-oriented programming, where we'll take a few deep dives into some relevant topics. A quick overview, we're going to go over some quick vocab, then go into decorators, and then we will take some time revisiting polymorphism with some operator overloading, and then we'll revisit inheritance, looking at composition, and then we'll wrap up going over the solid principles of object-oriented programming. So just some sort of miscellaneous concepts. Coupling is the degree of dependency between classes. Tightly coupled classes can be a lot harder to maintain, so you want to avoid this if you can. Cohesion, how well methods and properties relate to the class's goal. If something has high cohesion, it's a lot easier to maintain. Association is just the relationship between classes. You can have one-to-one, one-to-many, many-to-one, or many-to-many. A class attribute is a Python variable that belongs to a class rather than a particular object. It's shared across all instances of the class. However, if it's a mutable type, like a list, it can be modified on a per-instance basis. So watch out for that. Where we have that kind of goofiness. So just be aware when you're using class attributes. Any questions? Fantastic. Okay, decorators. What are they? They're a feature in Python that modify or enhance the behavior of functions or methods, and they're applied using that notation there. You've seen them. It's just that little guy up there. But what are they really? Well, they modify the behavior of functions without changing their source code. And decorators are implemented as functions that take another function as an argument and return a new function. And they can capture the variables from their enclosing scope using function closure. Common use cases will be input validation, authentication, logging, and caching. And they, in general, improve code modularity, readability, and maintainability, which are all things we love to do with object-oriented programming. So input validation might look something like this, where we raise a value error if we get any sort of input that we don't want to actually process in our function. Authentication could look like this. We can just enforce authentication checks before executing certain functions, making sure that only authenticated users do have access to sensitive operations. We also can make class and method decorators. Here's a little example of the syntax that we would use for that. I know it's a lot of text on this screen, but essentially we do get to just take this wrapper. We see it here applied to this output we would get. This is largely for reference. I'm not expecting you to memorize all of the syntax here on the spot. We can also use arguments with our decorators, which is very convenient. So we see here we have this decorator factory that lets us define here what level of logging we want. And then we can just go ahead and call that and have that all taken care of for us. Oh, a question, yes. Oh my gosh, they think I'm muted. Am I too far from the microphone? Is this better? On Zoom. I'm not. I see a thumbs up. I see two thumbs ups. Okay, I am awaiting. Okay, cool. Okay, I'll keep going then. Yes, okay, cool. Thank you for the heads up. All right, so Python has some built-in decorators that are very convenient. Static method, class method, and property are all common ones to see. Static method declares a method as a static method, which can be called on the class itself without needing an instance. and it does not have access to the class or instance attributes. So we see here, we can just define the math utility without then instantiating the object, and that can be pretty convenient. It's a pretty simple function here, but you can use it in very extensible ways. The class method declares a method as a class method, which receives the class itself as the first argument, and this can access and modify class-level attributes, which can also be very convenient. And then we have a property, which is really useful. Those of you who are a little more experienced with other languages might have seen this around. This lets us define a method as a property getter, allowing attribute access via dot notation rather than method invocation, and this can help us define setters and deleter methods for property manipulation. I really like this. It's just a very convenient way to make sure, say, when you are setting this new radius here, you can just have this bundled in automatically under the hood that, hey, we're not allowed to set any kind of value that just doesn't make sense for us. This is just a really convenient way to bundle up, making sure that all of your attributes will be exactly what you want them to be. And then we also have the data class decorator. This is a kind of recent one. This one can be very convenient. It's an excellent piece of syntactic sugar. If you just have an object that's mostly just serving to hold data in interesting ways beyond just a very simple primitive type, this is very convenient to use. It will kind of just be a lot more readable. It also, if you aren't using any type annotations, it is a very great way where you just do get them bundled in anyway, which is a sort of good gateway into starting to use those more in your everyday practice. There is some funkiness with some mutable values as default values, but generally you won't be running into that. Yes?
So is data class something we can store as information in a SQL database as well?
I would not be able to answer that. I don't use SQL databases, but perhaps someone in the room might have that knowledge. No, okay, I apologize. All right, so decorators can be chained, which is pretty useful also. Watch out for the order of execution. It will actually go first for the innermost decorator and then go up the list. But otherwise, they work the way you would expect them to, as decorators are just wrappers like that. Yeah. And now, we're going to go on to operator overloading unless we have any more questions on decorators. Great. All right, so how to and when to. And this is, again, a revisiting of polymorphism. On Monday, we went over the most common type, which is dynamic or runtime polymorphism or method overriding. All of these are valid names for it. And this is essentially when we have a superclass here and a method. If we weren't going to define that method in subclass 1, for instance, we would end up looking for it in subclass 1, but then just go up to the superclass and use this. However, if we go ahead and we use method overriding in subclass 2, this subclass, and we override the my method, when we go for grabbing that from subclass 2, we do end up with the overridden method as a quick review of how dynamic polymorphism works. But we also have another kind, static polymorphism. We did see this on Monday too when we defined the Dunder-Repper method for some of our classes. The Dunder-Repper method is a really helpful way to get a string representation of an object. And it knows how to handle some input types to make them readable just automatically. So we'll see here, if we do a repper on a dictionary, we'll get a nice sort of list of keys and values. However, it doesn't just automatically, magically know everything. If we try to use repr on some random class, it will oftentimes just give us a location in memory where we could find that class. So we use operator overloading on operators like this to go ahead and let it know how we want it to behave with this new and novel input. So now we've defined this here, and we've overloaded the operator, and we get to have a really nice representation of our class. Sorry. Other common operators to overload include these ones up on the screen. For instance, going back to our smoothie example, if we wanted to check equality between two smoothies, and I know this was a couple days ago, we had been storing the content as lists, which are inherently ordered. So we couldn't really just naively say, hey, are the contents of this equal to the contents of that? Because we never sorted them. So if we wanted to override our equality so that we could say, hey, is smoothie A equal to smoothie B, we might go ahead and implement this dunder-eq method and take like content, make it sorted, and then compare it with the other smoothie sorted. And that lets you kind of take these strange and novel data types and be able to just use normal operations on them in ways that you would expect. The same thing with add. If we wanted to add two data types, we might go in. For the smoothie example, we might just say, okay, we'll want to concatenate the contents of this smoothie with the contents of this one. That also is a logical way where we might implement an add operator. We can also override indexing, which is convenient. Say we had an object that was mostly just a wrapper for some data, plus some metadata stored in attributes. We could essentially create a little bit of syntactic sugar where we just bypass the .data index, and we're able to just say, hey, we just want to take this object and index straight into it. We know what we're doing. This is what we want. So it just lets us think about our objects and how we would use them with standard operators, and makes things more convenient and readable. However, we do have to think about, sure, we can do this, but sometimes maybe we shouldn't. I took this very succinct answer that I really liked straight from Stack Overflow, so big shout out to Peter, who says that you should only overload operators if it's the natural, expected thing to do and doesn't have any side effects. So say we had a Roman numeral class, it makes sense to overload addition and subtraction, sure, but you wouldn't overload it if it isn't natural. It doesn't make sense to define addition or subtraction for a car or vehicle object. So you never want another programmer to come in looking at your code and see operators being used in a way where they can't look at the expression and say, hey, I know what that's going to evaluate to. So if you're ever unsure, maybe it's better to just go ahead and use a method that you write. But if it's a logical thing, go ahead and overload the operators. Any questions on that? Fantastic. All right. So now taking a visit back into inheritance and why we might actually prefer composition. Let's first review inheritance. It is the mechanism by which one class can inherit properties and behaviors from another class. Benefits include code reuse, extensibility, and promoting a hierarchical structure, and we might imagine a car class inheriting from a vehicle class. And now composition is when we assemble objects piece by piece, and that's creating complex objects by combining simpler objects, which does enhance flexibility, encapsulation, and we get to kind of sidestep around really deep inheritance hierarchies where we just have one object inheriting from another, from another, from another. It gets crazy on some code bases. So a car, for instance, might be composed of all of these smaller objects instead. And just for a general sense of how that syntax looks, here we would have each of these objects well, the class is defined, and then we would go ahead and we would instantiate the objects, and then we would go ahead and use those in creating this car that is composed of these smaller objects. Then we could go ahead and we could access these methods that we have inside these other objects, which is a pretty handy way to go about it. But it is really important to recognize these as two different tools for achieving different goals. We need to think about containment as a has-a relationship. A car has an engine, and a person has a name, and so on, whereas inheritance is an is-a relationship. A car is a vehicle, a person is a mammal. And there is a saying out there where people will just say, hey, prefer composition over inheritance. You'll see that a million times on the internet. And yeah, it's important to remember that composition is something you should be considering, but it is best to follow a balanced approach where both inheritance and composition are used judiciously based on the specific requirements of each project. And then a quick note on mix-in classes. I'm throwing this in because this is not the most intuitive to me at first glance. These are technically multiple inheritance. So even though mix-in B seems less important than this here, our first class that we're inheriting from, we do have the C is a and the C is a mix-in B relationship. However, with method resolution order, or MRO, there is an ordering to the way that we go about our multiple inheritance. So we will end up with a mix-in, putting that second after the first class that we're inheriting from. So there is still an implicit hierarchy there. If you're ever unsure about what ordering you have for an object that does use some amount of inheritance, you can always use this operator just to take a look. Any questions on that? All right. So the solid principles of object-oriented programming. They are single responsibility principle, open-closed principle, the Liskov substitution principle, the interface segregation principle, and the dependency inversion principle. The SRP says that a class should only have only one reason to change, meaning it should have only one responsibility or job. And this improves readability, maintenance, and reduces coupling. And a car class responsible for managing its own state or behavior should be separate from classes responsible for logging or persistence. We don't want the car to have to go in and access a database and say, hey, here's all of my data, here's how I'm going to put this into this table. We just want the car to be paying attention to the car and what the car is doing. Then we could have a database manager dealing with the other side of things. The OCP says that software entities should be open for extension but closed for modification. I'm sure you all are kind of sick of me listing the same benefits that we see all over OOP, but this definitely does make things a lot easier and easier to maintain. And an example of this would be extending a rental management system to support trucks and motorcycles by defining a vehicle base class and then creating subclasses for each vehicle type, instead of going in and modifying existing source code in which we might then change our rental car management to then support motorcycles. Now, the LSP principle says that subtypes should be substitutable for their base types without altering the correctness of the program. And an example of this would be a rectangle class should be substitutable for a shape-based class without breaking the behavior expected from a shape. So there should never be methods and attributes in a parent class that are somehow weirdly missing from a child's class. You should always be maintaining that interface, and then if you want, adding to it. The ISP says that clients should not be forced to depend on interfaces they do not use. So imagine if we had a messaging application and we had different interfaces for email, SMS, and push notifications, we would only want, say, an email client to have to depend on the email interface. We wouldn't want to be cluttering it up with all these methods and dependencies related to SMS or push notifications. And the DIP says that high-level modules should not depend on low-level modules. Both should depend on abstractions. And by similar token, abstractions should not depend on details. Instead, details should depend on abstractions. The benefits of this are promoting decoupling and enabling easier testing and mocking and facilitating dependency injection. For example, implementing a payment service class that depends on a payment gateway interface rather than a concrete payment gateway class, allowing for easier testing and flexibility in swapping out different payment gateways. And then if you wanted to, you could swap in different payment gateways such as PayPal, Stripe, and Square, which allows the dependencies to still remain on the payment gateway interface rather than anything specific and tightly coupled, I guess. So this helps keep things very modular and logical throughout. So a review of the solid principles. A class should only have one reason to change, and classes should be open for extension but closed for modification. Subtypes must be substitutable for their base types. No client should be forced to depend on methods it does not use, and you should depend on abstractions and not concretions. Any questions? All right, that's our deep dive into these topics. Now I'm going to take a few minutes to set up for the overview for our next practice session or problem session, unless anyone has any questions that have come up. Yes?
What if you have a class that you want to... What if you have a class where you want its methods to... You have a parent class where you want its children to forcefully override its methods?
So an abstract method in the parent class? Yeah. Oh. Yeah. And if you wanted to, you could make the whole parent class be an abstract base class where everything there needs to be implemented by subclasses, which just helps create a unified interface over all of the subclasses you'll have. And we will, I did include that in this next bit that we're going to have, too, if we want to see how the syntax there looks. All right. Just going to unplug this while I go through all my my windows. Please feel free to talk amongst yourselves and talk about your favorite solid principle.
I also merged in a pull request with the slides, so now might be a good time to also pull things down.
So I'm just going to run us through kind of casually the degradation demo notebook in Rail, which we will be using as a sample for a toy pipeline that we will be building and extending using object-oriented principles after this. So essentially, the degradation pipeline is a pipeline that applies degradation. First, we start off by generating some data with a PZ flow, and then we go ahead and we apply these 4 Rail degraders to the data, which gives us a general sense of what real data might look like, because of course nothing's perfect, and certainly not the data we observe. So yeah, I feel a little bit like I'm preaching to the choir here, because you are the astrophysicists. So please bear with me for any of that, I guess. So we start off with, I guess, a lot of the a lot of the Rail complications. So the reason for our toy demo today is to just sidestep a lot of these dependencies that we have and that we know we should not encourage in our code. So we start off with the PZ flow. We just use the flow file, and we set up the data store. In Rail, the data store is essentially just keeping track of a lot of our intermediate data files. We will have a version of this in our pipeline as well. And now we generate a true sample here, and then we go ahead and we just take a look at it and grab the samples from it. And then we apply the first degrader. This one is going to be the most complicated. This is not the one that I recommend you all starting with, but this is a beautiful piece of code by John Franklin, where he step-by-step implemented all of the math behind the error model that LSST will be using. And then here we just have this wrapped in Rail. So this will be one of the problems that you all can work on. It'll be a bit of a scavenger hunt looking through documentation of LSST to implement what this is doing, or alternatively, you can look through his code and get a sense of what's going on from there. And this will add in these little U error, G error, et cetera columns into our data, which previously was just Redshift and the UGRI CY. And then we just go ahead and here we see little errors, which is very exciting. It works, that's fantastic. And then we just go ahead and we add on some of these next degraders. And as we go through and we make all these objects, then we get to go ahead and see how the data that we have is slowly getting cut down. This one is, I believe, a density true plot, so it doesn't quite show the scoops, but both are important. And one of the exercises will be implementing plotting in a more cohesive way in our pipeline. And so I definitely recommend creating an option for that going either way. And so basically, and then this one we aren't going to pay attention to in our pipeline. So this is basically, I guess, what's going on in our degradation demo pipeline. This is a time to ask any questions about it. Alex Small said he's also very happy to take any questions on Slack, although he does have meetings during this time, so they will be delayed your answer, but any time from now on doing the demo, he is open to any messages. So this is just a general sense of what we're going to be doing, and then in our demo notebook, we are implementing a Quail pipeline, Quail being short for quick rail. And here we have a very similar structure. I have simplified the dependencies, so all you'll have to do is create this Conda environment, install these packages, and go ahead and make a kernel for yourself. We grab our truth data from PZ Flow, and we have our truth data, and then we have here our Quail base classes. We're going to have three classes that I have implemented for you all. And here is an example of the abstract base class, which is our Quail stage. Every stage in our pipeline will be inheriting from this. This one has just a very simple structure. We just need to have a constructor, and we need to have the name, the data in, and the data out for the pipeline. Pretty self-explanatory, I would say. And then we have a run, which will run whatever this stage is trying to do. Here we have an example of a stage that does nothing, so we just connect the data out to the data in, and we are good to go. And here is our sort of mirror of the degrader demo. We have a bad error model instead of the LSST error model. One of your tasks will be to scoop this out or just copy paste and then add some extra things in here. Our error is just adding this, not a very good error, so I know you all can do better. Then we'll have similar things here. This one is mostly implemented. You could play with it. You could change it up a little bit. This one is an exercise for you all. You can feel free to reference what is there in the degradation demo notebook, look through the Rail code if you'd like, or implement it as described at the top of this notebook in whatever way you see fit for your science use cases. And then to make the pipeline, we have this data store object, which will just store all of the intermediate data files that we want. And we have this pipeline object, which in its run function will just go ahead and connect these stages sequentially. In Rail, that uses a SESI backend, which can deal with more complex graphs and things not being sequential. So there are far more powerful pipeline implementations that one can use, but for now, this is what we'll be using. And we have some functions here that you might want to go ahead and implement if you have time or you just need a little break from thinking through some of the other problems. And here we have an example of how we would set up the pipeline. We just put the input data in our data store, and then we just list out the stages that we want to use. We define the pipeline, and we can see here our data store is just the input data. We run the pipeline, and we get all of our intermediate data files with these shapes. At this point, this is where we're adding the error columns. So we get those extra columns, and then we end up with our output data. We can take a look at that just by poking around in the data store. We can see any of these here. And then note that we used operator overloading in the get attribute operator here in the data store, so we can just go ahead and use dot notation if we'd like. And for plotting, you might remember the really nice error plot here where things do seem to be a little bit different than here. So when you go ahead and implement your own LSST error model, this should start looking a little bit better. And then we go ahead and we do copy some of the other plotting code here where we can see, this is not a density, so we can just go ahead and see where we have gone ahead and cut with the quantity cut. As you make changes, this will change, and that can be a really fun tool to get a sense of what you're doing in this pipeline. And it can also be a really fun exercise to think, how would you go ahead and implement a plotting tool in your objects? What makes the most sense? Where would you want to put it? And maybe you try something, you write some more code, and you discover, hey, let's iterate on this, let's change it around. So I'm presenting all of these things as options to work on with a generally suggested ordering of things to explore. Here at the top, let me know if you have any questions. I'll be around, and good luck on your Quail pipeline.